The light produced by a laser has properties which are very different from those of ordinary sources. A light source such as a light bulb radiates light energy over a wide range of wavelengths, sending out pulses of light at random in unrelated bunches of waves. Laser light is different in that the atoms emitting light are synchronized by a process called stimulated emission. Stimulated emission takes place when an atom or molecule in an excited state is struck by a photon of an appropriate energy. The incident photon will stimulate the atom to make a transition to a lower energy level, and at the same time emit its own photon. The two photons leaving the atom not only have the same wavelength, but are also in phase. These photons can now strike other excited atoms, producing additional photons that are in phase with the original ones. In this way, a monochromatic beam of coherent light is produced. Laser action can be attained by using many different types of gases, liquids, or solids. However, one type of laser of special interest is the carbon dioxide laser. The great advantage of the carbon dioxide laser over other types is its large power output and relatively high efficiency. The CO2 laser consists of a long discharge tube filled with a low-pressure gas. A 100% reflective mirror is placed at one end of the discharge tube, while an 80% reflective mirror is placed at the other end. Energy is put into the system by means of a high voltage applied to the ends of the tube. Cooling water is circulated around the outside of the discharge tube in order to maintain a moderate temperature. For stimulated emission to occur, the carbon dioxide molecules must initially be put into an excited state. In order to excite the carbon dioxide molecule to the proper energy level, nitrogen gas is mixed with the CO2. The nitrogen is put into an excited state through collisions with high-energy electrons, which are generated from the electrical discharge. This energy is then efficiently transferred from the nitrogen molecules to the CO2 molecules upon collision between the two. An incident photon of the proper energy can now stimulate the CO2 molecule to emit a photon identical to the first. The system of parallel mirrors sends the photons back and forth through the gas many times, assuring that a great number of excited CO2 molecules are in fact struck by photons. An avalanche of photons is quickly created, producing a continuous beam of radiation. Because one of the mirrors is only partially reflecting, a portion of the radiation passes through it and escapes from the discharge tube. This forms the output beam of the laser. The carbon dioxide laser produces a beam not of visible light, but of infrared radiation. Although it cannot be directly seen, the effects of the beam's focused energy can be observed. If the laser beam is focused on a piece of wood, its kindling temperature is quickly reached as it bursts into flame. A point on a concrete wall receives such an intense amount of infrared radiation that it glows with a white-hot color. With 300 watts of power being supplied to the laser and operating at an efficiency of 20%, the power of the output beam is equal to 60 watts. This is thousands of times more powerful than a standard classroom helium neon laser.